Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson for intermediate thermodynamics, we'll be developing the Vant-Hoff equation, which is a way of looking at temperature variation in the equilibrium constant. So we've previously defined the equilibrium constant in terms of activities A as the exponential of negative delta G of reaction over RT is the product for all components of the activity to the stoichiometric coefficient power. And this is a function of temperature, but we've defined it specifically for the temperature of 25 degrees C and the pressure of 1 bar. What if we don't want to hold a reaction at 25 degrees C? What if we want to allow the temperature to vary? Well, we can see in this group with the delta G and T in the exponential that both of those are functions of temperature. If you recall, originally this was developed from looking at the partial molar Gibbs energies. I could also do it for pure species. I can do any of these and get similar sorts of results with some modest changes, mostly in notation as far as the visual goes. But I want to know how the G over T expression is going to change with temperature while I hold the pressure constant. And so I can just simply use a product or quotient rule, whichever way you like to think of it. And it's going to be how dg dt times 1 over t, okay, minus the g sub I divided by t squared, taking the derivative of the 1 over t. Okay, so far so good. But now remember, we have these definitions, and by definition, G is H minus TS. And I can do this lots of different ways, but since I'm working with the partial molar quantities, I can write it in terms of the partial molar quantities. I also have, from the fundamental relations, that dg dt at constant pressure is negative S. And I can write it using the partial molar quantities or the pure species quantities, whatever. So if we use these in our expression that we just wrote for how does temperature affect this ratio G of I over T, what I have is that this is going to be negative SI over T for this first group, and let me switch colors for emphasis, minus GI over T squared, where GI is HI minus TS squared. So minus HI over T squared plus SI over T. Now, these are the same but opposite signs, and so therefore we see that this is equal to negative HI over T squared. Okay, now let's combine this. Let's bring this back into our definition of the equilibrium constant. Again, keeping in mind that I can do these things in various ways, what I end up with is that if I want to see how this changes with temperature, the natural log of Ka, and I'm simply doing the natural log so that I can, let's just write that over here, natural log of Ka is negative delta G of reaction over RT. And so now then if I want to see how this changes with temperature, it's going to relate to how delta G over RT changes with temperature. So I have a spare R in the denominator, and this becomes 1 over RT squared, the squared right here, times the sum of my new I delta H of formation of I can go to that stage, or I can call it delta H of reaction over RT squared. Now the negative here combines with this negative here, so this is a positive. And I end up with what this is called the Vant equation, which says that d dt of the natural log of Ka holding pressure constant is the heat of reaction all over RT squared. And again, the Van 't Hoff equation. Now, a couple of things that I want to point out. One is that if delta H of reaction is negative, this is an exothermic reaction. If you look at this, what that's going to tell me is that as Ka decreases, the temperature needs to increase. That's a T. T needs to increase. If the heat of reaction is positive, or an endothermic reaction, as Ka increases, temperature also will increase. Now there's a simplified form of this that assumes that delta H of reaction does not vary with temperature, but is approximately constant over the entire temperature range. If we make this assumption, it allows us to do the integration and write an expression for Ka at temperature 2 compared to temperature 1 is equal to the negative delta H reaction over R 1 over T2 minus 1 over T1. And this negative came from the integration process. Now this is going to be appropriate if the temperature does not change too much. If we look at C sub P as a function of temperature, and we'll just use a simple cubic expression for that, then when the temperature is larger, I can use the heat of reaction at standard state and add this temperature change expression, so the integral of C sub P dt, and end up with a more complex but better expression for the relationship between Ka at T2 and T1. So the expression involves the integral of this C sub P. It's just an ugly expression, okay? But it's not really all that difficult. All these delta A, delta B, delta C are simply the stoichiometric sum of the coefficients for the pure C sub P's. And we can use this so that we can estimate K's for temperature changes when delta H of reaction is not at the standard state. So thank you very much for your time. We'll continue to look at examples and how also the pressure affects this in future videos.